All right, so let's look at this one. We're going to look at a electron going at a very fast speed, perpendicular to this path, right, at 1 million meters per second. And it's going to be in this field, which is 10 millitesla. It's a 10 millitesla field. This perpendicular makes everything nice, and so we want to figure out what the radius of this path is. Obviously, this is a job for a free body diagram, right? So what's going on here? Well, we've got a net force pointed inwards, right? That's going to be MAC. That's going to be a centripetal acceleration, if you remember those things. And then there'll be a force here that's going to cause that. Since this is the centripetal acceleration is a part of the net force, we have to figure out what this force is. This is actually, of course, the magnetic force, right? So we know what that is. So if we have our velocity this way and our field that way, right, then this should be the correct direction for force. Now this says it's going outward here, but this is an electron, and the electron has a negative charge, so the force ends up coming in this way. Because the electron's charge is negative, it reverses the direction. Okay, simple enough. So that's more or less how we start, and we want to use that free body diagram to find what we've got. So we have F equals MAC. F is QVB sine theta, which is 90 degrees. It's this direction. It's this angle here. And then that's equal to MAC. So that's the mass times the centripetal acceleration, which is V squared over R, which is the radius, which is what we want to find. Okay, so far that's fine. Then to do this, we can do all sorts of things. The best is just to wander through and start putting numbers in. 1.602 times 10 to the minus 19 coulombs times 10 to the 6 meters per second times 10 millitesla, 0.01 Tesla, is equal to the mass of the electron, right, which is, and this is E, right? That was what, 9.11 times 10 to the minus 31 kilograms. The velocity was still 10 to the 6th meters squared per second. 10 to the 6 meters per second squared, the whole thing. Over that R that we need. So we solve for R, we multiply R by both sides by R, right? Then we keep the 9.11 times 10 to the minus 31 kilograms here, as well as the 10 to the 6th meters per second squared. Actually, we get rid of one of those, we cancel this guy out. Then we divide by these guys, so we have a 1.602 times 10 to the minus 19 coulombs is 0.01 Tesla. So that's 9.11 divided by 1.602. Multiply that by 100 from the from this guy here, and we have 568 times 10 to the minus 31 plus 6 plus 19. So 19 plus 36 is what? It's 24. 25. Okay, 31 minus 25 is 6. So we have 568 times 10 to the minus 6 meters, which is 0.568 millimeters, about half a millimeter. So that's more or less where we end up with this one. So this one, really, we're just balancing forces. Well, not balancing forces. This is an unbalanced problem, right? It's a steady state problem, not a static problem. But basically, we're taking the forces and relating them to the acceleration to find the dynamics of the situation. And that gives us the radius of our electron's path. All right? Bye now.